to educator.com. Today we're going to be focusing on water. And water is essential to life. In fact, we're composed mostly of water. Organisms need water to survive, and marine organisms actually are immersed in water. So we're going to talk about water and some of its special properties, starting with the molecular structure of water. Water is given by the formula H2O, and it consists of one oxygen and two hydrogen molecules. It is a polar molecule, and if you need a review of the concept of polar and nonpolar molecules, then go back and look at the previous lecture. I talk about that in detail, but here I'm going to do a review. So remember that the electron pair shared between a hydrogen and an oxygen molecule is not equally shared. Oxygen is more electronegative than hydrogen, and that means that it more strongly attracts electrons. As a result, the electrons spend more time near the oxygen atom than they do by the hydrogen atom. This ends up giving oxygen a partial negative charge, or delta minus. And since the electron pair spends less time by the hydrogen atom ends up with a partial positive charge, or delta plus. Now, one important concept or theme in biology is that of emergent properties. Emergent properties are properties that emerge or come into being at higher levels of organization. For example, if you just took one heart cell and looked at it in a petri dish, it couldn't pump blood. But if you put many cells, cardiac cells together, they can pump blood. So that ability to pump blood is something that emerges when you put many cells together at a more complex level of organization. And we're going to see this all the way through the course. But here, if you take a single molecule of water, it's held together by covalent bonds. But if you put many molecules together, they hydrogen bond, and new properties emerge as a result of this hydrogen bonding. So looking back here at the single molecule of water, water is V-shaped, and because of that, and the fact that the oxygen is a partial negative and the hydrogen have partial positive charges, the overall molecule is polar, meaning one side is relatively negative and the other is relatively positive. Now, let's look at multiple water molecules associated with each other. Even though a particular hydrogen is covalently bonded to a certain oxygen, it also is attracted to nearby oxygen molecules. So here we have the delta negative, and on the hydrogens, delta plus. Even though this hydrogen is covalently bound to this oxygen, it's also attracted to a nearby electronegative oxygen molecule. And this attraction, shown by these dotted lines, is known as a hydrogen bond. Recall that hydrogen bonds are weak bonds, whereas covalent bonds are strong bonds. So a single hydrogen bond isn't going to do much, but many together can be strong, and they account for many of the special properties of water. In the natural world, you'll actually find water in all three of its forms. Liquid as water vapor. Liquid as liquid water. So liquid water. We'll also find the gas form, which is water vapor. And finally, the solid form, which is ice. In liquid water, the hydrogen bonds are constantly breaking and reforming with each other, whereas solid water, which is ice, that I'm going to talk about in a few minutes, is in more of a set structure, and that gives ice its specific properties. So let's go on and talk about some of these special properties of water. Water's special properties make it essential to life, and some of these properties are that water is both strongly cohesive and adhesive, that it has a high surface tension, and a high heat capacity, and a high heat of evaporation. Let's just take these one at a time. First of all, cohesion. Cohesion is the tendency of molecules to stick together. Water is highly cohesive. The reason it's highly cohesive is because of the hydrogen bonding. As I mentioned, adjacent molecules of water are held together by hydrogen bonding, so they stick together. Looking at how this can affect biology, when we talk about plants, we're going to talk about transpiration. This is the process by which water is drawn up from the roots of a plant all the way up through the plant and then evaporates out the leaves. And this can be hundreds of feet with a tree. So what happens is, as a molecule of water is lost from the leaf, as it evaporates, the next molecule gets pulled up. So one after another, these molecules of water pull each other up, and they do so through tubes called xylem, tubes that carry water in plants throughout the plant. So cohesion is one property of water that allows for transpiration. Now, adhesion is slightly different. This is the tendency of molecules to stick to other substances. So cohesion, water sticking to itself well. So it's cohesive. It's also highly adhesive and sticks to other substances. Tendency of molecules to stick to other substances. So not only is water cohesive, it's adhesive. And if we think again about the xylem, the water is being pulled up one after another by cohesion. It's also helped by adhesion though, because the water molecules adhere to the sides of the xylem. So if you look at a glass of water and you've ever seen a drop just sticking to the side, that's an example of adhesion. The water is cohering to itself, but it's also adhering to the side of the glass. Surface tension is a related concept. Water has a high surface tension, and this is what allows water bugs to actually walk across water. Surface tension can often be thought of as high surface tension substances can often be thought of as having like a film across them. And it's actually harder to break through that top layer, to break through that film, than it is to move around once you're in the water. So it would take more energy to break through the surface than it is to move once you're under. And the reason is because the oxygen, the water molecules are hydrogen bonded to each other. Underneath the surface of the water, each water molecule is surrounded by many, many other water molecules, and it has that attraction through hydrogen bonding to the molecules around it. At the surface, though, so underneath, there's molecules on all sides, and they're hydrogen bonding to each other. Now, if you look at this surface layer, though, at the surface, these molecules are attracted to each other and the ones beneath, but there's no water molecules above. Therefore, their attractive forces are concentrated among fewer molecules. So here, the attractive forces are dispersed among many molecules. Here, since there's no water molecules above, the bonds between the adjacent molecules and the ones below would be stronger. The result is that there's a stronger, the molecules right here are more cohesive than the ones underneath. And that accounts for the surface tension, the high surface tension of water. All right, we covered cohesion, adhesion, and surface tension. Now we're going to talk about heat capacity. Okay, so now we're going to talk about heat capacity and heat of evaporation. Water has both a high heat capacity and a high heat of evaporation. In order to understand heat capacity, we need to talk about the concept of specific heat. Water has a high specific heat. And that's what gives it its high heat capacity. Specific heat is the amount of heat a substance needs to absorb to increase its temperature. And being a little more exact about that, so it's the amount of heat a substance needs to absorb to increase the temperature of 1 gram of the substance by 1 degree Celsius. This is one way that we measure it. So just in general, specific heat talks about the amount of heat a substance needs to absorb in order to raise the temperature. But talking about it in specific units, one way to measure it is in calories, which is a way to measure heat, calories per gram per degree Celsius. So this is one way to measure specific heat. Okay, so looking at this a little more carefully. If something has a high specific heat, if this is a large number, then that substance is going to need a lot of heat in order for the temperature to change. So something with high specific heat is going to be harder to heat up. It's going to be harder to raise the temperature. It's going to require a greater input of energy. Water specific heat is specific heat of water is 1 calorie per gram per degree Celsius. And that is actually a relatively high specific heat. Let's look at it in different units that are commonly used. A joule is another unit that's used to describe energy. And specific heat's often given in joules per degree Celsius per gram. So let's compare some different substances using this measure. In this measure of units, water has a specific heat of 4.18 joules per calories per gram. Compare that to, say, lead. Lead only has a specific heat of 0.13, and ethanol, alcohol, 2.44. That means that it would take twice as much energy, almost, to raise water, 1 gram of water by 1 degree Celsius as it would for the ethanol, and 40 times more to raise water by 1 degree Celsius than it would to raise the lead. And this is very good for life because if we were comprised of a substance that had a low specific heat, then as soon as it got a little bit hot outside, inside our body would more easily heat up. So specific heat is measured as I've shown, and water has a high specific heat, and the result is a high heat capacity. So this was background to understanding the high heat capacity. High heat capacity means a substance, you can think of it as a substance can absorb more energy or more heat, because heat is energy, with a smaller change in temperature. So something with a high heat capacity can absorb a lot more heat than something with a low heat capacity and still maintain its temperature. Looking at this with a concrete example, if you're cooking and you have a metal pan and the handle's metal as well, within a few minutes you are not going to want to pick up that pan without a pot holder because you'll burn your hand. That's because metal has a lower heat capacity. So as soon as you turn on that burner and the heat gets on the metal, the temperature of the metal is going to rise. What you want is a handle that has a low heat capacity because that same amount of heat will be absorbed by the handle. The temperature of the handle won't change, or it won't change very much, and then you can touch the handle. Thinking of water that way, marine life live in the ocean, and they're a lot better off being in a substance that has a high heat capacity because even if it gets very hot out, it's a hot summer day, it's 100 degrees out, the ocean's not going to suddenly heat up. Or conversely, if it cools down, the water temperature will still not change or fluctuate as much. And that's not just for organisms that live in the water, but since most organisms are mostly made up of water, again, to keep our internal temperature constant, it's important that we're made out of a substance that has a high heat capacity and doesn't just have these big fluctuations in temperature. Okay, so that was heat capacity, and now let's talk about heat of evaporation. The heat of evaporation, or sometimes it's called the heat of vaporization, has to do with converting water or a substance from its liquid form to its gas form. And this has to do with the amount of energy it would take to convert from liquid to gas. If something has a high heat of evaporation, it's going to take more energy to get the molecules moving quickly enough in order for them to break free of their hydrogen bonds and form a gas. That unites the concept of both the heat capacity and the heat of evaporation. It has to do with the speed the molecules are moving at. Because looking at actually the concept of temperature, temperature is actually due to kinetic energy. So temperature is the average kinetic energy of the particles of a substance. Heat is energy, so molecules with a greater kinetic energy that are moving faster, they will be hotter, and they will have a higher temperature. Therefore, let's think of what this has to do with hydrogen bonding. Water molecules are hydrogen bonded together. In order to heat up water, you need to get the molecules to move faster. In order to get them to move faster, you have to break the hydrogen bonds, and that takes extra energy. And that's why water has a higher heat capacity and a higher heat of evaporation. Because if you're talking about a substance that's not hydrogen bonded together and you add some energy, those molecules are going to speed up right away. Whereas with water, first you have to use some energy to break the hydrogen bonds, then you can start speeding up the molecules. Therefore, to raise the heat of something or to get it to vaporize, you need to add energy. And you need to add more energy when a substance is hydrogen bonded together like this. So again, the special properties of water are really closely related to the hydrogen bonding that occurs. Recall that one mechanism that we use to cool ourselves is sweating. And what sweating is the conversion of water from its liquid form to its gas form. It's the evaporation of water from our skin. In that process, water absorbs heat, and that is what's going to cool us down. One more property of water that's very important that's not listed here, but that is related, is the fact that ice is less dense than water. In other words, the solid form of water is less dense than its liquid form. And this is an unusual property. In most substances, the solid form is more dense than the liquid form. And this is another property that makes water very important, especially for life in the ocean. So thinking about hydrogen bonding, if the molecules are moving more quickly, then the hydrogen bonds are going to break. And in liquid water, the bonds are constantly breaking and reforming. And then when those bonds break, eventually, if things are moving fast enough and enough of those bonds break, then water can vaporize. So that's as things speed up, the hydrogen bonds break. Let's look at the opposite. The freezing point of water is going to be 0 degrees Celsius. So as water gets cooler and cooler, as the temperature drops, that's going to mean that the average kinetic energy is less, and kinetic energy is the energy of motion. So as the temperature cools, the water molecules are going to move more slowly. The more slowly they move, the more chance to hydrogen bond. Eventually, they're going to get to the point where they form hydrogen bonds with the 4 adjacent water molecules. And this ends up forming a very stable lattice type structure where the different water molecules, would be bonded to each other, and they'd form a lattice. This is just really schematic, but if they're forming a lattice, and let's say there's a water here, a water here, a water here, a water here, and they're in this regular formation, this lattice structure is going to hold the water molecules at a certain distance from each other, and it holds them a bit farther apart than they would be in their liquid form. And that's why ice is less dense than water, because the water molecules form a lattice structure through hydrogen bonding to 4 nearby molecules. As a result, ice is actually about 10% less dense than water, and ice floats. Because it floats, animals, fish living in, say, a frozen lake will be insulated. So that layer of ice is going to form insulation, and it's going to prevent the change in temperature in the dead of winter. So this formation of ice and the fact that ice floats because it's less dense than water is another property of water that makes it essential to life. In the last lecture, I introduced the concept of molarity and just briefly talked about solutions. Now we're going to cover this in detail. First, some terminology. A solvent, when we talk about solutions, first of all, we're talking about a homogeneous mixture formed by combining a solvent and a solution. So homogeneous means it's dispersed equally throughout. So if you just take a rock and throw it in a glass of water, that's not a solution because it's not a homogeneous mixture. A solvent is the liquid in which the substance is dissolved. So if I have a glass of water and I put some sugar in it or salts, then the water here would be the solvent. And let's say I had salt, sodium chloride. That would be the solute. So the solute is the substance that's being dissolved. The solvent is the one that does the dissolving. This mixture altogether is called a solution. Water is a very good solvent for many substances, but recall that it's polar. So water is polar, and since like dissolves like, polar substances are going to dissolve well in water. Non-polar ones will not. So polar dissolve in polar. Non-polar dissolve in non-polar. Like dissolves like. Looking at an example of this, let's look at glucose. This is the structure of glucose. Glucose is a polar molecule. It has these hydroxyl groups that are polar centers, and on these groups you have oxygen with the partial negative delta minus and hydrogen with delta plus. Water we already talked about. Also has a polar structure, delta plus on the hydrogen, delta minus, so partial negative charge on the oxygen. So since these are polar, these two are attracted to each other, and what'll happen is water can dissolve polar molecules and also ions, because they have a positive and negative charge, by bonding to them and then forming what's called a hydration shell. This hydration shell is going to separate out the molecules in the solute. So let's say I dissolve glucose in water. I just drop a lump of glucose into water. These water molecules are going to be attracted, and the glucose will be attracted to the water, and eventually it's going to separate out the glucose molecules from each other, and these are going to disperse until they're evenly distributed throughout the water. Nonpolar molecules don't have this same attraction for water, so they aren't going to dissolve well in here. Like dissolves like, so if you take a teaspoon of oil, drop it in water, you're going to watch it separate out. Even if you stir it, it's just going to separate right back out. Because hydrophilic molecules, you'll hear this term, or water-loving, are polar. So glucose or sodium chloride, which is dissociates to form sodium, which is charged, and chloride, these are ions. So then the polar water molecule is also partially charged. These are going to be attracted. So hydrophilic molecules are polar. Hydrophobic are nonpolar, like lipids. And this is very important in biology. We're going to see when we talk about the cell structure that the cell membrane, because it contains many nonpolar lipids, large polar molecules can't cross the cell membrane without help. And that's important in regulating what gets in and what does not get into the cell. So polarity also accounts for certain properties of the cell. When we discuss solutions, we discuss sometimes whether they're acidic or basic, or acidic or alkaline. Acids can be thought of as substances that increase the concentration of hydrogen ions in a solution. Bases decrease the concentration of hydrogen ions in a solution. And just to add to this, one common way for bases to accomplish this is bases may do so they might increase the hydrogen ion concentration in a solution by increasing the hydroxide ion concentration. All right, so let's just look at water. Water can actually have an acid-base reaction. It can dissociate into hydrogen ions plus hydroxide ions. So it would actually be, and if you look, it's all balanced. We have 2 hydrogen, 2 hydrogen, and 1 oxygen. When it dissociates into ions, when this hydrogen pulls away, it actually leaves behind its electron. So this hydrogen ion leaves behind its electron and becomes positively charged. You end up with a positively charged hydrogen ion, and the OH that's left behind has an extra electron, so it's negatively charged. Just for a moment, to be clear though, this is actually not going to just float around by itself. What's going to happen is it's going to be associated with another water molecule. So there will be another, H2O, and this is actually in a form that it's bound to that, and it forms what's called a hydronium ion. But for simplicity, we're just going to refer to it as hydrogen ion. It disassociates into hydrogen ion and hydroxide ion. But you should know that in reality, this is not floating around loose usually. It's part of a hydronium ion. Okay, so overall though, water mostly exists in this state, H2O. So this reaction, the equilibrium is very far to the left, and water is actually neutral. However, some substances like to dissociate, and they do dissociate, and they are therefore very acidic or very basic. Water mostly exists like this, not a lot of loose hydrogen ions and hydroxide ions floating around, so it's pretty much neutral. Let's look at what's called a strong acid. A strong acid is one that's going to really have a reaction where it completely wants to dissociate. Hydrochloric acid, HCl, so this is hydrochloric acid, is a strong acid. It dissociates to form hydrogen ions and chloride ions. And the reaction equilibrium is to the right. So if I took a cup of water and I threw some hydrochloric acid in it, this is going to dissociate, and there's going to be a lot more hydrogen ions floating around, and that is going to increase the concentration of the hydrogen ions in the solution. So since this is increasing the concentration of hydrogen ions in the solution that I make, it's an acid. And it's a strong acid because it dissociates almost completely. Let's look at a base. Let's look at a strong base to start with. KOH, potassium hydroxide. This is going to dissociate to form potassium ion plus hydroxide ions. Now, as I said, bases may increase or may decrease the concentration of hydroxide ions indirectly through the formation of hydroxide. So a base dissociates to KOH. Then the hydroxide combines with hydrogen ions that are floating around to form water. The result is going to be a decrease in the concentration of hydrogen ions. So again, a base decreases the concentration of hydrogen ions in a solution. It can do so directly or indirectly. Here it's happening indirectly, but we recognize that when we see something dissociating to form a hydroxide ion, the end result is going to be decreasing the hydrogen ions. So acids raise the hydrogen ion concentration, bases decrease. Sometimes we call these acids hydrogen ion donors because they increase the level. And sometimes we'll call bases hydrogen ion acceptors because they will accept a hydrogen ion and thus decrease the concentration of hydrogen ions. So you can think of it as this as base as accepting, the base is accepting a hydrogen ion, an acid is donating a hydrogen ion. Another example is ammonia, and let's look at what happens with this. This is a base. Now, it doesn't form hydroxide ions. In fact, it actually lowers the concentration of the hydrogen ions directly. It is a hydrogen ion acceptor. Ammonia will combine with hydrogen ion to form ammonium. So in doing so, it directly lowers the hydrogen concentration, hydrogen ion concentration in a solution. For example, if I had water and I threw some ammonia in it, that ammonia would bind with these hydrogen ions and form ammonium, and I would end up with a solution that is more basic because it's lower in hydrogen ion concentration. Just some properties of acids that you might hear about. Acids turn litmus paper red. We're going to talk about pH and pH paper and measuring pH, which is a way of measuring how acid or acidic or basic a substance is. So acids turn litmus or pH paper red, and they tend to taste sour. An example would be lemon. Lemons are acidic. Bases turn litmus paper or blue, pH paper, they turn it blue. They feel slippery. They taste bitter. An example would be soap. So I said that bases feel slippery, just like if you think about what soap feels like, it's very slippery. Buffers are very important in organisms because buffers resist the change in pH. If you added hydrochloric acid to a solution, the solution is going to become more acidic. If you add hydrochloric acid plus a buffer, the acidity will change less than if you just added the hydrochloric acid alone. So what these do is they minimize changes in the concentration of hydrogen ions. And they do this by they accept hydrogen ions when an acid is added, and they donate hydrogen ions when a base is added. So they resist change. Our blood has a pH of around 7.4, and if the pH goes out of that range, it can be very detrimental to life. So in order to prevent that change, we have buffers. Very important buffer in our blood is carbonic acid, H2CO3. This is carbonic acid. And this is a weak acid. And its corresponding base, it dissociates to form H plus bicarbonate, HCO3 negative. So most buffers are weak acids and the corresponding base, or weak bases and the corresponding acid. And I'm actually going to, with weak acids and bases, we show the reaction going in both directions, because unlike with strong acids, just want to completely disassociate, these don't. The reaction's going back and forth. So let's think about this. If the blood becomes too acidic, that means that the concentrations of hydrogen ions is too high. What bicarbonate will do is it'll bind to these hydrogen ions, and this reaction will move to the left, and carbonic acid will be formed. So you can think of it as absorbing the excess hydrogen ions. Now let's say a base is added to our blood. The base is going to decrease the concentration of hydrogen ions. The buffer will minimize that change or mitigate it by dissociating and thus donating hydrogen ions. So buffers resist change in pH by donating hydrogen ions if needed or accepting them if needed. So they're going to go the opposite way of whatever, if you've added an acid, the acid increases the hydrogen ions, the buffer will take those up. If you add a base, the hydrogen ion concentration decreases, the base will donate. So it does the opposite to keep things stable. Now I've mentioned pH, which you've probably heard of before, but let's go into some detail about this. pH is a scale that we use to describe how either acidic or alkaline a solution is. And it's on a scale of 1 to 14. Neutral is right here at 7. Distilled water would be here at 7. So pH, it's often paper, and you can dip it into the solution and then look at the color change. And like I said, acids are on the red end, and then bases are on the blue end. If something is more basic, more basic or alkaline, equals a higher pH, which equals a lower concentration of hydrogen ions. So hydrogen ions move in the opposite direction as the scale. Less hydrogen ion concentration, more basic, higher pH. More acidic. Remember that if something's an acid, it donates hydrogen ions, so more acidic equals a lower pH, and that is going to equal a higher concentration of hydrogen ions. So the scale moves the opposite way as the concentration of hydrogen ions. Just to give you some examples, stomach acid is around here in the 2 to 4 range. So most of our body, the pH is around 7.4. So blood is right here at around 7.4. Water, distilled water, is at 7. Stomach contents, stomach acid, is in the 2 to 4 range. So it's acidic, and the enzymes in our stomach work very well at that low pH. Vinegar is an acid. Vinegar is around 3. So vinegar is around 3. It's acidic. A base would be, an example would be baking soda. That's a base. And that has a pH of about 9. It's important to know that this is a logarithmic scale. That means that if I'm looking at, say, vinegar with a pH of 3, and then I measure some stomach acid and it has a pH of 4, the difference between these is actually pretty large. It's actually 10 times. So a pH of 4 is 10 times more basic than a pH of 3. Or you could say the pH of 3 is 10 times more acidic than the pH of 4. If I went from 3 to 5, it would be 10 times 10 or 100. So each unit is a 10-fold difference. And the reason we measure it this way is that there is a very wide range of how acidic or basic a solution can be. And in order to just have a nice condensed, compressed scale that's not going to be humongous, we use logs just to condense it. And then we can show a big range on just a small scale. pH actually is the negative log of the hydrogen ion concentration. At a pH of 7, what you have is 1 times 10 to the negative 7th moles per liter of hydrogen ions. So this is hydrogen ion concentration, and right here at 7, we'd have 1 times 10 to the negative 7th. If we went up, or if we went down 1, then it would be increasing the hydrogen ion amount by a factor of 10. Okay, so again, pH, important points. Low numbers are acidic. High on the pH scale is basic. Acidic represents a high concentration of hydrogen ions. Basic represents a lower concentration of hydrogen ions. Water is neutral at around 7. This is a logarithmic scale, so moving 1 unit translates to a 10-fold difference in how acidic or basic or in the hydrogen ion concentration. All right, starting with example 1. How is the shape of a water molecule related to many of the special properties of water? Recall that water is V-shaped. Many of the special properties of water are due to the fact that it is polar. This polarity allows for hydrogen bonding with nearby oxygen molecules. Because water is V-shaped, one side of the molecule ends up being relatively negative and the other relatively positive. Oxygen is electronegative. It attracts the electron pair more strongly than the hydrogen. It has a partial negative charge. The hydrogen atoms have a partial positive charge. Therefore, it's polar. This end of the molecule is relatively negative. This is relatively positive. If it were a linear molecule, it would not have this polar nature. Because of this polar nature, hydrogen bonding occurs. Hydrogen molecules, atoms that are covalently bound to one oxygen are still attracted to other nearby oxygens because these are also partially negatively charged and they form hydrogen bonds. So the polarity of water allows for hydrogen bonding, and it's this hydrogen bonding that accounts for many of the special properties of water. List 5 special properties of water. So we talked about why these properties exist. So what are they? Well, first of all, water has a high heat capacity. It also has a high heat of vaporization, or you could call it heat of evaporation. So it takes a lot of heat, a relatively high amount of heat, to change the temperature of water, and it takes a relatively high amount of heat to change water from its liquid form to its gas form. Water is strongly cohesive. Water molecules stick together. Water is strongly adhesive. Water molecules also stick to other substances pretty well, very well. It has a high surface tension. Because of the hydrogen bonding at that surface layer, it's a little bit harder to break through the surface layer. And that forms essentially a film, can be thought of as a film across the water. In addition, the solid form, which is ice, is less dense than the liquid form of water. This is because of the stable lattice structure that's formed by hydrogen bonding at low temperatures. The result is that ice floats. The solid form of water floats on the liquid form. So these are 6 properties. This only asks to name 5, but any 5 of these would have sufficed. Lemon juice has a pH of 2. Milk has a pH of 6. How many times more basic is milk than lemon juice? Okay, so pH of 6, that's milk. So we could say 6, 5, 4, 3, 2. And over here at a pH of 2 is lemon juice. So lemon juice is more acidic than milk, and milk is relatively basic. It's more basic than lemon juice. So this is asking how much more basic, or you could have phrased it the other way, how much more acidic is the lemon juice. Because this is a logarithmic scale, each unit represents a 10-fold change. So going from 2 to 3 is 10. 10-fold, 10 times. 3 to 4 is a 10-fold change. 4 to 5, and then 5 to 6. So going from 2 to 6, I'm going to be increasing 10-fold, times another 10, times another 10, times another 10. So that gives me 100, 1,000, 10,000. So that's a very large range, and this shows you why we need to use a logarithmic scale, because it wouldn't be very practical to try to fit these wide ranges onto a scale that was just a linear scale. Which of the following are acids, which are bases, and why? Remember that acids increase the hydrogen ion concentration. Bases decrease the hydrogen ion concentration. So let's look at this first one. This is showing the dissociation of a substance into, this should actually be 2 H pluses plus SO4 2 minus. Since this is dissociating to form hydrogen ions, it's increasing the concentration of hydrogen ions to the solvent it's added to. Therefore, this is an acid. And this is actually sulfuric acid. And it dissociates to form sulfate plus hydrogen ions. HNO3 dissociates to form H plus NO3 minus. Again, since this is dissociating to form hydrogen ions, it's increasing the concentration of hydrogen ions, and therefore it's an acid. This is the strong acid, nitric acid. And it's dissociating to form hydrogen ions plus nitrate ions. Okay, here we have NaOH dissociating to form Na plus OH minus. Recall that another way to look at bases is that they increase concentration of hydroxide ions. And then the hydroxide ions bind to hydrogen ions to form water, and that in turn decreases the hydrogen ion concentration. So you can think of a base either as just something that decreases hydrogen ion concentration or that increases hydroxide ions. Since this is increasing the concentration of OH minus, it's a base. And this is a strong base, sodium hydroxide. Sodium hydroxide dissociates into sodium and hydroxide. Here I have the arrows going both ways because these are weaker bases, so the reaction's not so far to the right. Now let's look at what's happening with this one. It's dissociating to form, so these are weaker acids or bases. We have to figure out which one. This is dissociating to form a hydrogen ion plus this other compound. Increased hydrogen ion, I have an acid. This is a weak acid, it's acetic acid. Acetic acid dissociates to hydrogen ions and a compound called acetate. Finally, Na2CO3 plus water dissociates to form 2 sodium ions plus, this is bicarbonate and hydroxide. So I can see with this increase in the hydroxide, what I have is a base. And this is sodium bicarbonate, which is a weak base. It dissociates to form sodium, bicarbonate, and hydroxide. So again, here we have an acid, sulfuric acid, another acid, nitric acid, and a base. This is a strong base, sodium hydroxide. A weak acid, acetic acid, and a weak base, sodium bicarbonate. And we define which are acids, which are bases, and why in terms of what they do to the hydrogen ion concentration. So that concludes this lecture on the properties of water, and I will see you again soon.